Okay, so first let's remember that the effect of a dielectric is to weaken the electric field. So if our original electric field is E naught, then our new electric field with a dielectric is E naught divided by some constant kappa. So that's the effect of a dielectric. Well, now let's look at a parallel plate capacitor without a dielectric. So here's our capacitor. We'll say this plate is positively charged. This plate is negatively charged. And we don't have a dielectric. We'll draw a Gaussian surface here. And we're going to look for the electric field here. And I'll call this E naught. That's our original electric field without a dielectric. Now our Gaussian surface includes just the positive charges on this top plate. There's no electric field at the top because we're inside a conductor. There's no electric field on the side, so we're just looking for this electric field here, E naught. And we know from Gauss's law that the integral of E naught dA is going to equal Q enclosed, that's enclosed, over epsilon naught. Now if we have this nice parallel plate capacitor, we know that E naught is going to be constant here, then the integral of E naught dA is just going to be E naught times the area of that plate. The integral of dA is A, and that will equal Q enclosed over epsilon naught, and Q enclosed is the charge on this capacitor. And so E naught, our original electric field without the capacitor, is Q, the charge on the capacitor, divided by A, epsilon naught. Okay, so now let's make a new capacitor that does have a dielectric. So I'll draw it over here. I always tend to run out of room on these things. So here's our here's our capacitor. Positive charge up here. Same charge, so I'll put the same charge on it as we had up here. So we have charge Q. We'll make that a plus Q. And now we're going to fill this with the dielectric. And so the dielectric will have some negative charge here. Okay, so now I'm going to make another Gaussian surface. Well, let's see if I can be fancy here. Probably not. Red. Okay, so we'll make our Gaussian surface here. So our free charge is plus Q, and it's going to enclose this other charge here, and I'll call this other charge Q prime. Okay, now again from Gauss's law, we know that the integral of E dot dA equals Q enclosed over epsilon naught. Once again, our field here is going to be E. Now I'm calling this E. This is E, our new field with the dielectric. And so this E naught was the field we would have without a dielectric. E is the field we'd have with the dielectric. So Q enclosed now equals Q, the charge on the capacitor, minus Q prime. So this equals Q minus Q prime over epsilon naught. And so EA equals Q minus Q prime over epsilon naught. So I just took the integral there. And so E, our new electric field with the dielectric, equals Q minus Q prime over A times epsilon naught. Okay, so that's what you would expect. But then you'll notice that E naught equals Q over A epsilon naught. We got that up here, so that's from that. We also have this over here. And so we can now say that, let's see, what do I want to say here? That E, so I'm taking this E, replacing it with this E naught, I'm sorry, replacing this E naught with this equals Q over kappa A epsilon naught. Okay, so now I have E equals Q minus Q prime over A epsilon naught. And I have that that is also equal to Q over kappa A epsilon naught. Now, if you compare these two things, then you can see that Q over kappa has to equal Q minus Q prime, because what's left is 1 over A epsilon naught. So that's why including the kappa in the integral takes care of the charge on the dielectric. So now that's why we can say that the integral of kappa E dot dA equals Q, because Q over kappa equals Q minus Q prime.